This is part 2 of a 3-part series on the Cayley-Purser encryption algorithm, key generation. If some hypothetical person Alice would like to send a secret message to another hypothetical person Bob using the Cayley-Purser algorithm, Bob would act as the key generator and generate the public and private keys in Cayley-Purser. He would then send the public key to Alice while retaining the private key for further use. To generate the public and private keys, Bob first does something really familiar. He generates two large prime numbers p and q and computes their product n, the identical first step that Bob would take if he and Alice had decided to use RSA encryption for their clandestine communications instead of the Cayley-Purser algorithm. Next, Bob considers the general linear group of 2x2 matrices with integer elements and modular arithmetic modulo n, denoted like so. Now, there are several things here that warrant some explanation. So firstly, what is a general linear group? A general linear group of degree n is defined as the set of n by n invertible matrices together with the operation of matrix multiplication. It is denoted as GLNF, where n is the degree of the general linear group, and f is some specified field. So as it turns out, there are quite a few things to explain here as well. So firstly, the degree n of a general linear group is just going to specify the size of the matrices that we're going to be working with. For example, let's say I specify a degree of 2. Then I know I'm going to be working with 2x2 matrices because of this n by n specification. So for example, I could be working with a matrix like 1, 2, 3, 4, which has 2 rows and 2 columns. I could be working with a matrix like 3, 6, 8, 9, again with 2 rows and 2 columns. So the degree just tells me what sort of matrices I'm going to be working with. And if I decided I wanted to work with 2x2 matrices, I'd denote the general linear group, like so, substituting in a 2 for the degree n, and working with some field f. Secondly, what are invertible matrices? An n by n matrix A is said to be invertible if A times the inverse of A is equal to the identity matrix, or A inverse times A is equal to the identity matrix. Flannery decided to use 2x2 matrices for the Cayley-Purser algorithm. So in the case of 2x2 matrices, the identity matrix is defined as the 2x2 matrix where entries on the main diagonal are all 1 and all other entries are 0. A little more simply put, I is equal to 1, 0, 0, 1. Now, if A is a 2x2 matrix with elements of, say, A, B, C, and D, then we compute A inverse as 1 all over AD minus BC times this matrix, where A is the top left element, D is the bottom right element, B is the top right element, and C is the bottom left element. AD minus BC is called the determinant, and you can see that if AD minus BC does not equal 0, then A inverse will exist. But if AD minus BC does equal 0, A inverse will not exist, because we'll have 0 in the denominator. Therefore, we say that A is invertible if the determinant AD minus BC does not equal 0. Now I'd like to talk a bit more about specifying the field, denoted F. I mentioned a bit earlier that Bob would consider the general linear group of 2x2 matrices with integer elements and modular arithmetic modulo n as part of his key generation. Now this with integer elements and modular arithmetic modulo n portion is what is going to help us determine the field F. Firstly, this with integer elements portion specifies that the elements in our matrices have to be integers, no decimals or anything of that nature. Secondly, this modular arithmetic modulo n portion specifies that the elements in our matrices are limited to the resulting integers that are obtained from taking any integer mod n. This idea is a bit easier to grasp with an example. If I specify the degree lowercase n to be 2 and uppercase n to be 5, then I know firstly that I'm working with 2 by 2 matrices, and secondly that elements in my 2 by 2 matrices are limited to the result of any integer mod 5. If I take any integer mod 5, the only results that I'm going to get are 0, 1, 2, 3, or 4. Why is this? Well, let's say I evaluate the expression 25 mod 5. 5 goes into 25 an even 5 times, so the remainder of this is 0. So 25 mod 5 is equal to 0. Okay, then let's say I try 24. 24 mod 5. 24 divides 5 evenly only 4 times, and then I get a remainder of 4. So 24 mod 5 is equal to 4. If I do 23 mod 5, I then get a remainder of 3. 22 mod 5 is equal to 2, and 21 mod 5 is equal to 1. And then 20 mod 5 is once again equal to 0. This pattern is going to continue on and on and on. So if I take any integer mod 5, I'm always either going to get 0, 1, 2, 3, or 4 as a result. So once again, if I choose my degree, lowercase n, to be 2, I know that I'm working with 2 by 2 matrices. And if I choose my uppercase n to be 5, then I know that the integer elements in my 2 by 2 matrices are going to be limited to the result of any integer mod 5. In other words, the elements in my matrices are either going to be 0, 1, 2, 3, or 4. Two such 2 by 2 matrices whose elements are limited to the integers 0, 1, 2, 3, or 4 are the matrices 0, 1, 2, and 3, and 1, 2, 3, and 4. This final portion of the definition of a general linear group of degree n, the together with the operation of matrix multiplication, means that I would take two such matrices like these and then multiply them together. Now, matrix multiplication can be a little unintuitive. Compute the product of these two matrices. We're going to first work with the first row in the first matrix and the first column in the second matrix. First, multiply 0 by 1 and add 1 times 3. Zero times 1 plus 1 times 3, of course, equals 3. So 3 is going to be the top left element in the product matrix. Next, we'll work with the first row again, but this time the second column. So we're going to do a similar procedure. First, multiply 0 and 2, and then add 1 and 4, 1 times 4. The result of this is, of course, 4. So 4 becomes our top right element in the product matrix. Now we'll deal with the second row in the first matrix and the first column. We're going to do 2 times 1 plus 3 times 3, which of course gives us 11. And then we're finally going to work with the second row in the first matrix and the second column in the second matrix. We're going to do 2 times 2 plus 3 times 4, which gives us 16. Going to create a new matrix from this matrix by taking each of the elements in this matrix modulo 5. So 3 modulo 5 is just 3, 4 mod 5 is 4, 11 mod 5 is 1, and 16 mod 5 is also 1. So this is going to be our final matrix. The general linear group of 2x2 matrices is made up of lots of matrices like this, with integer elements and modular arithmetic modulo n, if n equals 5. So back to key generation. Bob is going to consider the general linear group of matrices with degree 2, with integer elements and modular arithmetic modulo n. Bob will then pick 2 matrices, chi and alpha, from this group such that chi times alpha does not equal alpha times chi. In other words, such that the matrices are not commutative. Bob will then pick a natural number r and compute chi inverse times alpha inverse times chi, the result of which will be called beta. Bob will also compute chi to the r power, the result of which is known as gamma. Bob has now finished key generation. We'll publicly release the values of n, alpha, beta, and gamma. He will retain the value of chi. This is what he's going to use for decryption later on. Alice will use the public key values that Bob has released to encrypt a secret message that she wishes to send to Bob. She'll send this encrypted message to Bob, who will then decrypt it using the decryption key of chi. But more on that in the next video. Thank you for listening.